First, I will talk about some examples for Westergaard stress functions. These are given in the book by Sanford. It's the appendix of the book. It's entitled and abbreviated Compendium of Westergaard Stress Functions. Westergaard.pdf. There are solutions for different types of crack problems here, and you can use these functions to derive full stress fields. From the outset, we have talked about inverse method or inverse solution, and the functions, these were derived, they satisfy the boundary conditions to appropriate area stress functions. And then you can use these to calculate stresses at all points in the complex plane. And certain idealized geometries are also included. It starts with this here, referred to as case G6. Again, an infinite plane containing a semi-infinite crack. Under crack face loading, loads or forces per unit length are applied on the crack faces. They can be applied separately. For example, if Q equals 0, there is mode 1 loading. Crack face force here is P. And what's the Westergaard function for mode 1 loading? It's given here, Z1 equals 1 over pi P times 1 over Z plus B times square root of B over Z. Now, this is sufficient. This single function is sufficient to find all stresses and the stress intensity factor at the crack tip and the displacements. In the homework, you will work on such derivations. But if P equals 0, then you have mode 2 loading, a shear force acting on the crack face, and Westergaard function is Z2, and this Z2 will have defined, again, all quantities. All full-field quantities and asymptotic quantities, everything is known once the stress intensity function, once the Westergaard function is given. These Z tildes are actually Z bars, as they were shown as Z tilde in the book. In our notation, that's Z bar. And these are the integrals of these Westergaard functions, and they will help find the displacement field. Z bar functions are required. But stress intensity factors are given anyway. Without doing any computation, you can directly use the stress intensity factors, K1, for example, for this problem. And idealized crack shape as well. There is nothing else as semi-infinite crack. However, if it is a surface breaking crack, and if its length is large, you can approximate it as a semi-infinite crack. But mode 1 stress intensity factor is square root of 2 over square root of pi b times P. P is force per unit length in plane elasticity. But I will ask you to derive the stress intensity factors. And K2 is also given. And under mixed mode loading, both of them are non-zero. Therefore, various solutions are available in this compendium. And find these different cases, distributed loads. It's theoretically possible to find this case from this case. Because it's a Green's function for this case, but distributed load multiple or double cracked specimen, let's consider the other cases, internal cracks. This is a crack under remote moments. That was the problem we have dealt with. Crack in infinite plane. Under normal stress or shear stress. If it's under normal stress, the problem is mode 1. It's under shear, it's mode 2. Westergaard functions and stress intensity factors, sigma pi a, sigma square root of pi a, tau square root of pi a. A basic problem in fracture mechanics. Now, you can examine these other cases as splitting forces acting on the crack face. Double forces, this is in the homework. Distributed load on crack surface. These are crack surface loads. They could be useful in examining limit loading problems as well. If we have time, we can cover the Buckner's principle. Periodic cracking to this is periodicity W, full crack length 2A, and so the cracks are interacting here, and this will cause somewhat larger stresses and stress intensity factors. Periodic cracks with concentrated forces, and you can examine these yourself, given in the book. And if one of these is given, if the Westergaard function is given, you'll be able to, the good part is that you'll be able to find full stresses or asymptotic stresses, whichever you want. An example on the application of Westergaard method. An internal cracking in infinite medium. These are elasticity parameters, mu and kappa, loaded by a pair of splitting forces at x equals b. B is the coordinate here. Crack face loading, referred to as crack face loading. Concentrated forces are applied on the crack face. What are the stress intensity factors? That is the question. Derive the stress intensity factors. But one thing you should notice at the outset are the stress intensity factors equal to each other. Stress intensity factor at x equals a and minus a. Are they equal? That's the question. At the crack tips, are the stress intensity factors equal? They are not equal because loading is not symmetric. Which means that you have to find separate intensity factors for A and minus B. And how can we do this? For the inverse solution, this is case 510, not 511, not the double force, single force. Case 511 is in the home. Yes. Case 510 in Westergaard compendium of stress functions. And this is given, therefore, in the book by Sanford. Let's choose the correct marker. Westergaard function, z p over pi, square root of a squared minus b squared, z minus b times z squared minus a squared. This is available, and that could be your starting point for a mode 1 problem. We did all these derivations. A, the stress function phi, is real z double bar plus y times imaginary z bar. Sigma y was calculated as real z plus y times imaginary z bar. These are analytic functions defined in the material plane that is constructed as the complex plane. Now, it's not necessary to know the stress distribution on the cracked plane. Y equals 0. And we know how this is computed on the cracked plane, equivalent to x squared minus a squared for x greater than a, minus x squared minus a squared for x minus less than minus a. And at y equals 0, sigma y becomes real z. Stress intensity factor depends on sigma y. And for that reason, we are considering sigma y. And for sigma y is real z, and real z, then for x greater than a is p over pi times this over x minus b times square root of x squared minus x squared. This is real z for x greater than a, and this is real z for x less than minus a. Only a sign difference. Applied definition of the mode 1 stress intensity factor, K1 at a. Limit x goes to a, 2 pi x minus a, sigma y by x comma 0. Which means that you need this expression here. Substitute and carry out simplifications to remove the singularity. Since x is not a, they are cancelled out, and evaluate the limits and simplify. We will end up with this expression for the mode 1 stress intensity factor. P over square root of pi a times square root of a plus b over a minus b. Now, this is a general result for stress intensity factor to crack tip A. Now, what's the stress intensity factor at the other crack tip? And as I mentioned, these are not equal. Now, the problem is not symmetric. Therefore, you need to consider the definition for the other crack tip definition, the stress intensity factor. So note that we are not using asymptotic relations. We are making use of full fields, exact solutions in this case. K1 at minus a is limit x goes to minus a minus square root of 2 pi minus x minus a sigma yy. Procedure, right now it's an algebraic procedure. Substitute this into the definition. Carry out the simplifications. And after a final simplification, you will find K1 at minus a. Stress intensity factor at a and at minus a. Now, what's the common feature here? If b equals 0, then they have to be equal, because if the splitting forces act at the origin, then stress intensity factors are equal because of symmetry, and you can see that by substituting 0 for B. We can easily show that K1 equals K1 K1A equals K1 minus A. That is P over square root of IA. A somewhat simple result. An interesting feature of this loading is that as crack length becomes larger, there is a drop in the stress intensity factor. It is not like remote loading. Stress intensity factor is getting smaller and smaller as the crack length becomes larger. Because crack tip is moving away from the force, so that's probably the reason. Any questions about this derivation? And this shows that if for a certain geometry, Westergaard function is known, the problem is already solved, but you should know the relations between different unknowns to be able to find that solution. You can find either full field or symptotic representations. You can find the stress intensity factor. And the most important variable in the whole problem is the stress intensity factor, as we will see later. That was an example or illustration for the Westergaard stress function. And another case or an extension of this definition, keep in mind this geometry of an internal crack loaded by these concentrated forces. And the question is, can I solve the same problem for a distributed load? I can see the similarity between these two. Here we have the same geometry. The crack is in infinite plane, but instead of concentrated forces here, it's loaded by a distributed force. And can we derive the solution for the distributed crack face loading or an internally pressurized crack in infinite plane? Can we derive the solution by using the concentrated force result? That's the question. And it's of course possible because concentrated force solution is referred to as Green's function. If a Green's function is known, the solution for distributed loading can be derived by integration. Well, it is going to be a matter of integration because over an infinitesimal zone, you can find a concentrated force resulting from this distribution. But it's done here or shown here is the crack under distributed load over dx. Then forces acting on the crack are dp on both sides, and dp is sigma dx. I can integrate stress intensity factor due to sigma dx. So find the stress intensity factor due to the whole distribution. And how is this done? How is this done? Replace force by sigma dx in the original result. Sigma dx over square root of pi a. Crank length is not changed, but B now becomes the coordinates of the concentrated force. This becomes the new X. I replace P by sigma dx and B by X. And then integrate it from minus A to A, because this is dk1. This is the differential of k1 because of sigma dx, and can be integrated from minus A to define the position A to find stress intensity factor. Therefore, we have an integral whose integrand is given by the Green's function. And this integral can be calculated. Just move these constants through the integral sign, sigma over square root of pi a. The resulting integral is minus a to a square root of a plus x over a minus x dx. This is a problem from calculus. This integral can be found by trigonometric substitution, but I am not going to know details. The result is pi a, and I have also found the result by maple as well. Symbolically, you can integrate it by maple or MATLAB. It's pi a. Therefore, substitute pi a, and you will end up with this result, the familiar results. And this is the fourth time, I guess, we are ending up with this familiar result, sigma times square root of pi a, stress intensity factor. This is another important problem. A crack internally pressurized with sigma, and stress intensity factor for this crack is sigma times square root of pi a. Its stress intensity factor for this case is equivalent to the stress intensity factor calculated for the crack under uniaxial loading. This is uniaxial loading. The stress intensity factors are the same. Green's function approach for the calculation of the stress intensity factor, and this approach is applicable for variable loads as well. The load could have been variable like this. A linearly varying pressure acting on internally on the crack surface. The method is essentially the same, however, the integrals are different. And this is the method for the application of Green's function.